Okay, so we have this picture where we need to find tension 1, tension 2, and tension 3, given the figure here. So what's the first thing we want to do? Very good. Mark, what's going to be our free body?
The hanging mass.
Okay, so how many free body diagrams are we going to have? Two. All right, so we're going to do the box one first, all right? So raise your hand and let me know what the forces are acting on the mass. Mark? Which way? Down. Very good. Okay. And is that it?
No.
Is there something else touching that hanging mass, Mark? What is it? Okay, so what kind of force? Which way?
Up.
He's trying to he's trying to get on that video there.
I don't know what you're
All right. So we've got the force of tension 3. Now, is there any acceleration of that hanging mass? No. So what does that mean then? Yes, it is an equilibrium. So what does that mean for our forces?
None of them have acceleration.
What's equal? Very good. The force of tension must be equal to the force of gravity. Okay. So what is the force of gravity equation? Mass times little g. Very good. Do we have the mass of the hanging mass?
Yes.
Which is?
5.
That's a naked number.
5 kilograms.
There you go. 5 kilograms times 9.81 meters per second squared. Okay, so then what must tension 3 be equal to with the correct sig figs? You should all have your calculators out by now. Shabam? 50 newtons. Raise your hand if you agree with Shabam. 50 newtons. Excellent. Mm-hmm.
So is that it?
No, that's just one of the tension forces. Now we got to find out what T1 and T2 are. Okay, so let's see here. What can you tell me about those other tension forces in the problem? Somebody other than Mark. Somebody other than Shabam. Brady.
Hang on.
Adam. Very good. Those other tension forces do not lie on the X or Y axis, which means you have to do what? Very good. We must decompose them. Okay? All right. So now the question becomes, how do we decompose a vector? I knew people. Isaac. Wow. Brady. Yeah, SOHCAHTOA, okay? We're going to decompose with SOHCAHTOA. All right. Okay, so we have this vector here, and we have this vector here. That means we're going to have an x component of the T1. We're going to have a y component of T1. There's going to be an x component of T2, and there's going to be a y component of T2. Okay? So if this angle up here is 20 degrees, what must this angle down here be? 70, okay? All right. And then if this angle up here is 60 degrees, what must this angle here be? 60 degrees. There you go. Okay. Now, let's see. Let's go ahead and do our decomposition. So I want to know T1x. All right. What do we use with the x? Mark? Cosine. Very good. So T1x is going to be equal to T1 times the cosine of what? 60. Very good. We don't know. That's something we're trying to figure out. That's a variable. So T1y is going to be equal to what? Very good. T1 times the sine of 60 degrees. Okay, now let's get T2. So if I want T2y, what's that going to equal? No, 70. And then I want T2x, so that's going to be what? Very good. Okay, so that's a bunch of equations. I also want to redraw my free body diagram now that I have decomposed those. So let's get some space. All right, so I'm going to have a T1x this direction. I'm going to have a T2x in this direction. I'm going to have a T1y in this direction, and I'm going to have a T2y in this direction. And finally, I have a T3 in that direction. Does everybody agree with all of that? Okay, so now what do you see about our x-axis here? What do you notice? Okay, we have two opposing forces. Is anything happening to that knot in the middle? Is it accelerating? It's not moving. So what can you say about those two forces? They must be equal and opposite. Very good. Okay, so that means we can say that T1x must be equal to T2x. All right. And then what can we say about that y-axis there? It's also in equilibrium, which means that T2y plus T1y is equal to T3, which was equal to, are we going to use our rounded number or the actual? All right. So that, I believe it was 49.05 newtons. It's a really bad 5. Cool. Okay, so yay, we know some stuff now. Let's say we want to figure out what T1 is, okay? We know that T1, where are we at? T1x, that had a previous equation, right? We just wrote it down on the other page. What is T1x equal to? Cool, so let's plug that in. Let's say T1 times the cosine of 60. And that right there is T1x, okay? Must be equal to, now let's do T2x, okay? What would T2x's equation be from the other page? Okay, T2 times the cosine of 70. All right, now I want to just solve for just T1, all right? That's all I want to know, T1. So what can I do? Okay, let's divide by cosine of 60. That'll get T1 by itself. That's true. It's very, very true. Yeah, he totally glitched on me, so. Where are you at? Wait, what? Over here? That? That's a 60. Mm-mm. Y'all are stupid. All right. Now. Really? Wow. Okay. Now, cosine of 70, cosine of 70 and cosine of 60, those are numbers, okay? That's actual value. So I want to go ahead and get an actual numerical value. So type into your calculator right now, cosine of 70 divided by cosine of 60. And then I'll call on somebody in a minute. Where's your calculator? Where's your calculator? Let me get you one.
You gotta give her two.
I need your shoe. I didn't stutter. So I get my calculator back. All right, let's see here. Cassie.
0.6840402867
No,
kilograms.
no, there's no unit there. Just that number. All right, so all of that stuff times T2. Okay. All right. So okay, so we have our equation then of T1. T1 is equal to all this stuff times T2. Okay. Now let's see if we can figure out how to solve for one of those other equations. We've got T1y plus T2y equals 49.05 newtons up above. So let's go ahead and start plugging that stuff in. If we wanted to do T2, what would we, or T1, what would we plug in up there? Okay, because we have, again, we have T1, where's my pen? T1y plus T2y equals 49.05 newtons. Now, right here where we have T1y, how did we get that? How did you get T1y?
T1 times sine of 60.
Okay, it's times the sine of 60 degrees. So what I'm going to actually do here is I'm going to make a substitution, all right? I know that T1 is equal to this stuff right here, correct? So I'm going to plug all that stuff in where I see T1 and then multiply by the sine.
Yeah, that's T1. Not T1.
No, we divided. Remember? Look up above.
We divided cosine.
So we divided the cosines away, which left T1 by itself. Okay? So all of this right here, that is equal to T1. Okay? So, no, it's T1. Okay. So we're going to take all of this stuff and we're going to plug it in for T1. And then in order to get the Y part of it, we still need to go on ahead and multiply by the sine of 60. So we're going to say T2 times the cosine of 70. If you want, you can use this decimal number right now instead of doing what I'm about to do, which is just keep it in terms of cosine stuff. Okay, so all of this, that's T1, and we're going to multiply that by the sine of 60, and that will make it T1y. Everybody cool with that? Plus, now we need T2y, so that's going to be T2 times the sine of 70, and all of that is still equal to 49.05 newtons.
Wait, is that T2 or T2y?
This right here, all of this is T2y because we have it multiplied by the sine of 70. Okay? Now, our entire equation is now in terms of T2. There's no T1s in there, right? So if we can just group like terms, then we can solve for T2. That's why we made these substitutions right here, is so we could get a T2 down in this equation and get rid of the T1. Does that make sense to everybody? Okay. Because this equation, we can't do anything with it. We have two unknowns in there, and one's a T1 and one's a T2. But because I made a substitution and got everything in terms of T2, I now only have one unknown variable in my equation, which means I can solve. Does that make sense to everybody? Okay. So now let's go ahead and combine stuff. So you already got this value right here. Now you can multiply it by the sine of 60.
I have a question.
Hold on. I don't know, like right here, this sine over cosine, that's tangent. So if you wanted, you could do the tangent of 60 times the cosine of 70 if you want. I mean, there's all kinds of different ways you could do it. All I'm saying is let's reduce this stuff, okay? What's up, Adam? Yes. Yeah. Okay. Desire, did you have a question? No? Okay. So here's what I want you to do now. We got a value for this stuff a little bit ago, right? And now I want you to multiply it by the sine of 60 and tell me what that is, please. Somebody raise your hand.
Oh.
Garrett. 62655. Okay, plus, now somebody do just the sine of 70. I need to know what that value is, please. Okay, and all that stuff equals 49.05 newtons. Okay, now let's combine like terms. So if I want, I could, like factor, these numbers out and add them together, or factor the T2s out and add the numbers together. So that's ultimately what's going to happen. I need you to take this number right here, and I want you to add it to this number right here. Okay. All right. Who's added those two numbers together? Garrett? 1.532088. Whoa, rapid fire. 1.32088. 1.5320888. Okay, cool. So then all that stuff is multiplied by T2, and it's equal to 49.05. Now we're almost there. How do I get T2 now? Okay, divide by this number. Yep. Okay. Mark. Yes. The final answer.
30.
There you go. 30 is a naked number, Mark. Newtons. Very good. 30 newtons. Okay. 30 newtons there for T2. Everybody okay with this?
No.
What's wrong, Shabam?
All this substitution.
We'll walk back through it here in just a minute. I want to get the last one, and then I'll go back through it with you, okay? Yeah. What? Okay. So now we want to solve for T1, okay? So yeah, we had a little bit ago, we had come up with an equation that said that T1 was equal to 0.68404.02867 times T2, okay? Now, are we going to use this rounded version of T2, or are we going to plug in the full number? We need to use the full meal deal. Very good, okay? So go ahead, multiply the full T2 number by this value right here. This one, remember, that was the cosine of 60 divided by the cosine, or cosine of 70 divided by the cosine of 60, or something like that. Okay? Graham? Yes, please. T1, 20 newtons. Okay? All right, let's go back through all of this and see if we can figure out how we got where we ended up. Okay? Yes.
The equation where we did.
Okay. Adam?
Where do we get the 0.68404?
70. Yeah. All right, let's go back through and look at all of this, okay? So, starting right here, when we got our new free body diagram with all of our decomposed vectors on there, we saw in the x-axis that t1x is equal to t2x, and we have t2y and t1y must equal t3, which was 49.05 newtons, okay? Now, t1x has its own equation, so that's where we came down right here. We said t1 times the cosine of 60. That is t1x. All of this right here, that's t1x, right? Okay? And we know that that's equal to t2x, which is what this stuff is right here. That's t2x. Everybody with me still so far? And then I wanted t1 by itself. I just want to know what t1 is. So in order to do that, I divided both sides by the cosine of 60, which left t1 alone. Everybody okay with that? All right. So that means that t1 is equal to t2 times the cosine of 70 over the cosine of 60. And for easy purposes, we went ahead and got a numerical value right here, which is what we ended up using at the end of the video just now. Okay. Then we went back to that second equation in the y-axis where we have t1y plus t2y equals t3, and I just went ahead and said 49.05. And I can't do anything if I've got a t1 and a t2 in there because I don't know either of those things. But since I just solved for t1 up here, I made a substitution of all of this stuff. All of this stuff right here, that is t1, right? And we know that t1y is t1 times the sine of 60 degrees, right? So I plug all of this stuff in. This stuff right here, that's t1. All of this is t1. And then right here, when I multiplied it by the sine of 60, that's turning it into t1y. Everybody still with me? The reason that we have to turn it into t1y is because that's what we have up here. t1y plus t2y equals this stuff. Okay? So then right here, we've got t2y. That's what this is over here. t2 times the sine of 70 degrees. That is t2y. Okay? And then, of course, all of that is still equal to 49.05 newtons. Everybody still with me on this so far? Okay? So then you can do that cosine of 70 divided by the cosine of 60, and that gets you this value right here. Then we did the sine of 70. That gets us this value over here. Everything's in terms of t2, so now we can just add like terms, right? It's like saying 2x plus 3x. You would get 5x, right? Here we ended up with this much of t2. Then we can divide and solve for just t2. Then you take your answer, go plug it back into an original equation, and solve for t1. We good? Okay. Yes. I can. After Shabbat. What's up?
You see how we did the cosine and stuff for the left side?
Uh-huh.
T2 times cosine 70. Why don't we figure out cosine stuff for the right side?
Are you talking about this right here? In here?
Yep.
What about it?
So we did cosine 70 and cosine 60 and cosine sine. I get that.
Okay.
But then why didn't we do cosine on this side? Like, shouldn't there be cosine plus 2?
No, because it's equal to 49.05. This is still a different term over here. You could turn that into a numerical value, which is what we did down here on the bottom.
What do you mean break t2 up into the like cosine over cosine? Like we did with the first one.
I guess I'm not understanding that question.
Like
Why
on the
are
left side is t2 times cosine of 70 over cosine of 60.
Yeah.
On the right side is just t2.
Yeah, all this stuff right here, that is just T1.
Right.
Okay, and then by multiplying it by the sine of 60, that turned it into T1Y.
Because you're trying to solve for T2.
Correct.
So what if you were trying to solve for T1 first and just do the opposite?
Yeah, then you would have then back up here, instead of solving everything for T1 right here, we would have solved this equation for T2.
So you would have divided by cosine 70.
Yeah, we would have divided by cosine of 70, and that would tell us what T2 is. And then down here in this equation where we've got T2y, we would substitute in all that stuff right here, and all of our equation would then be in terms of T1 instead of T2. Okay, so it just depends on which one you wanted to go for. Adam? Yes. Good question. So right here, if I want to, I'm gonna roll over here real quick. If I have, like, let's just make it easy. Let's say I have 4 times T2 plus 3 times T2, okay? And that equals some stuff, right? 5. Okay? So if I wanted to, if I look at my algebra here, I can factor a T2 out front, can I? And that would be T2 times 4 plus 3 equals 5, right? And so that would be T2 times 7 equals 5. Does this make sense to you? Okay, that's all that we did, except instead of 4 and 3, we just had weirder numbers. Okay, all right, Mark. One of those original equations that we had. Like you could do it like T1x equals T2x. You could plug it in up there. Or where we have T1y plus T2y equals 49.05 newtons, you could plug it in up there if you wanted to. Yes, sir. Yeah. Juan. All right. Okay, so a 2-kilogram book is pressed against the wall horizontally with a meter stick. The wall has a coefficient of friction of 0.3. What horizontal force does the meter stick have to apply to prevent the book from sliding down the wall? What's the first thing we want to do here? Graham. Perfect. Free body diagram. Very good. So, let's see here. Somebody tell me all the forces acting on the book. All right, Isaac. Which way? Down. Okay. Okay. Very good, because that book's touching the wall. Which way? Very good. Friction must be the thing opposing gravity, otherwise the book would fall down, right? So what kind of friction do you think this is? This is static friction. Because that one is kinetic. Oh, my bad. All right, cool. So that's my free body diagram. Now, the question says, what horizontal force, so what thing are we actually looking for here? FA. We want the applied force. What horizontal force do you have to apply to prevent the book from sliding down the wall? And then, of course, it gives us our coefficient of friction, okay? All right, so what axis are we playing with? The x-axis. What do you want to do? F-net statement. All right, so we're going to say F-net in the x-axis is equal to what? What kind of acceleration? In the x-axis. Very good. Now, what's the acceleration of the book in the x-axis? 0. So all that's 0. Okay? All right. Now, what's the next F-net statement? Very good. What are all the forces? Very good. Force applied minus the normal force. Okay? Good. All right. Now, what do I do? Set them equal. So I can say that the force applied minus the normal force must equal to 0. So what does the force applied equal? No. Normal force. Force applied equals the normal force. Do you know the normal force? No, we don't. So that means we are now trying to find the normal force. Here's a logic idea. Or actually, I guess I'll let you guys try to come up with that. Use your Sherlock powers, your deductive reasoning. How can we come up with the normal force? What is the normal force related to? Friction. Very good. So what axis should we play with? The y-axis. All right, so We're going to do our F net statement then in the y-axis. What's the first one going to say? Mass times acceleration. What kind of acceleration? In the y-axis. What's that equal? 0, because that book's not moving. All right. So it's not. Okay. What is the second F net statement? Sum of all the forces. What would that be, Adam? Yes, because friction's up, gravity's down, right? Okay, so we're going to do our static friction minus the force of gravity. Okay, so now what do I do with those two? Set them equal. So we're going to say then the force of friction minus the force of gravity is equal to 0 newtons, which means the force of friction equals what? What does it equal? Force of gravity, okay. It has its own equation, right? What is it? M times little g. Very good. So we're going to say the static friction equals, what's the mass of the book? What's the mass of the book? 2 kilograms, right? Okay, 2 kilograms times 9.81 meters per second squared equals 19.62 newtons. Everybody there so far? You good with that? Okay, now static friction has its own formula, doesn't it? Or friction itself has a formula, right? What's the formula for friction? No, that's for the mu. I want the force friction's formula. Perfect. Okay, mu times the normal force is equal to friction, and we know that friction is also equal to this 19.62 over here. Perfect. What is the mu in this case? 0.3, all right? So we can say 0.3 times the normal force equals this force of gravity over here. Divide by coefficient of friction. What? Good. All right, so what's the normal force then? Is that everything? Okay, nice. All right, which must be equal to the force applied. So that means the force applied is... How many sig figs? Did you say 7? 70. 70 newtons.